Hello, welcome to today's lecture. And in this lecture, we are going to deal with the very important theory about lattice heat capacity, that is Debye theory. We will discuss all assumptions of the Debye theory. Then we derive the formula for lattice heat capacity according to Debye theory. And after all, we will see the accurateness of the theory with the experimental facts of lattice heat capacity. As we have already studied Einstein's theory, and we found that the theory fails at very low temperature, where Einstein's theory predicts that lattice heat capacity is proportional to exponential of temperature, while experimental facts shows that the lattice heat capacity at very low temperature is proportional to T cube. Now, what was the reason behind failure of Einstein's theory at low temperature? And it was the oversimplified assumption, oversimplified model of the solid, where it is considered that each atom or each quantum oscillator is vibrating independent of the other. In other words, the coupling or interaction between the vibrating atoms is not considered by the Einstein theory, and hence, due to this oversimplified assumption, the theory leads to failure at very low temperature. In 1912, it was Peter Debye who considered the coupling between the vibrating atoms, and in this way he considered solid as a continuous elastic body. Thus, here there will be no independently vibrating quantum oscillators, but here it is a continuous elastic standing wave, and the internal energy of the solid will reside in the elastic standing waves, not in the individual vibrations of the atoms. So, the important difference between Einstein theory and Debye's theory is that in Debye's theory, the coupling between the vibrating atom is considered, due to which solid now assumed as a continuous elastic body. One important difference, and another difference is that now the energy does not reside in the individual vibrations of the atom. Internal energy does not reside in the individual vibrations of the atom, but it resides in the elastic standing waves. Now, important is that the energy contents in the elastic standing waves can be quantized, like the quantization of energy of electromagnetic waves in a cavity. So, internal energy of the solid reside in the elastic standing wave, and again that can be, the energy content can be quantized. So, the quantum of vibrational energy in the elastic standing waves is named as a phonon. The phonon is the word similar to the photon in light, where quantum of energy in a light is recognized as photon. Photon travels with the speed of light, while what about phonon? Phonon will travel with the speed of sound, and it was due to the elastic nature of the waves. You can observe the elastic standing wave in this light as shown in the figure, where you will find that due to interaction between the vibrating atoms, the elastic standing waves, it is produced in the whole solid, okay, and the internal energy is assumed to reside in these elastic standing waves, and the energy contents are quantized, and quantum of vibrational energy in elastic standing waves is recognized as, or is known as, a phonon. Now, let us find the number of elastic standing waves in a specific wavelength range, and for that purpose we use Rayleigh's formula. According to Rayleigh's formula, the number of elastic standing waves in the wavelength region lambda to lambda plus d lambda, that means in the wavelength region d lambda in a solid per unit time is given by n lambda d lambda equal to 4 pi d lambda upon lambda raised to 4. Now, if v is speed of the wave, the relation between wavelength and frequency nu is given by v equal to nu lambda. Accordingly, we find lambda and d lambda as shown here, and after substitution of values of lambda and d lambda in equation 1, we obtain the formula for number of elastic standing waves in the frequency range nu to nu plus d nu. That means equation 1 represents number of elastic standing waves in the wavelength region d lambda, while equation 2 represents number of elastic standing waves in the frequency region d nu, and which is equal to 4 pi nu square d nu upon v cube. Now, here important change is that there are two types of elastic standing waves occur in solid. One are of longitudinal type traveling with speed vl, and other are horizontal with speed vt. And there are two directions of polarization again for the wave traveling with speed vt, and in this way we can modify the formula for number of elastic standing waves in the frequency range nu to nu plus d nu as here simply we have to put, so here it is 1 upon v cube, and this will be now 1 upon vl cube plus 2 upon vt cube by considering two directions of polarization for the transverse wave, and the formula in this way for number of elastic standing waves in the frequency range nu to nu plus d nu will be equation 3. Now, what about average energy per standing waves? Average energy per standing waves is again taken directly from the black body radiation, and according to black body radiation, average energy E bar per standing waves is h nu upon exponential of h nu by kt minus 1. So, this we represented as equation 4. So, with the knowledge of having number of waves in a wavelength range due to nu plus d nu and average energy per oscillator as E bar, we can find the energy in a solid or energy contained in the solid having number of waves in the range d nu as equal to n nu d nu into E bar. Now, if V0 is volume of kilomole of a particular solid, then total internal energy U is given by U equal to V0 into total number of energy of total number of waves, that is integration 0 to nu m n nu d nu into E bar, and this is whole multiplied by volume, that is V0. After putting the values of E bar and n nu d nu from this equation 3 and equation 4, so simply the difference is that here it is nu square, so and here it is h nu, so it will be h nu cube d nu and everything. So this and this factor will came there, and we find the expression for internal energy as shown in this figure. Now, important to note the upper limit of integration here. Upper limit of integration is the frequency nu m, okay, and it is the maximum frequency nu m. It is not infinite in this case. What does it mean? It simply means that there should not be infinite number of standing waves in a solid, or the solid would have a finite energy. It should not have infinite energy. So this is the important factor we have to recognize here. Then Debye used one assumption that is famous by his name, Debye's assumption. And what is that assumption is? According to Debye's assumption, the total number of standing waves in volume V0 is equal to total degrees of freedom in a kilomole of solid. We know that in a kilomole of solid, number of atoms are equal to Na, where Na is Avogadro's number, and each atom has 3 degrees of freedom, so there will be 3 Na degrees of freedom in a kilomole of solid. And according to Debye's assumption, total number of standing waves in a volume V0 of kilomole of solid is equal to 3 Na degrees of freedom in a kilomole of solid. So we have 3 Na equal to total number of waves in volume V0, so that will be equal to V0, 0 to nu m n nu d nu, and after substituting value of n nu d nu here, okay, and we get a factor 4 pi V0 in this bracket, and this is independent of nu and taken out of integration, and integration we have only nu square d nu. Integration of nu square, that will be nu cube by 3, and after putting the values of upper and lower limits, we find it is simply equal to nu cube by 3, nu m cube by 3, and in this way we have the expression given by equation 6, that is 3 Na equal to 4 by 3 pi V0 in bracket and bracket close nu m cube. So this is from the Debye's assumption. Now from this we can find the value of nu m cube, and similarly we can derive the expression for nu m, that is maximum frequency, and we can obtain the important factor that we have to substitute in the next coming steps, that is 4 pi V0 in this bracket, and that is equal to 9 Na upon nu m cube. After getting these three factors, we will substitute, we will obtain the expression for internal energy of the solid, that is energy of kilomole of a solid, and that will be simply equal to U into this, and after solving the integration, after putting the value of the factor here 4 pi V0 in bracket as equal to 9 Na upon nu m cube, and after putting this in this equation of internal energy, we obtain the expression 10 as the final expression for internal energy. Now it is only the thing that is remain to differentiate this formula for internal energy with respect to time, and after differentiating, but before differentiation we have to substitute here h nu by kt as equal to x, and after putting h nu by kt equal to x, that means nu equal to kt by h into x and d nu equal to kt by h into dx, and by putting h nu m by k equal to theta, where theta is Debye characteristic temperature. Here it is another temperature which is defined by Debye, that h nu m by k, where nu m is the maximum frequency of the wave in the solid. So h nu m by k equal to theta, and this is theta is known as Debye characteristic temperature. Now after using the values that h nu by kt equal to x, then nu, d nu and theta in the equation for internal energy, we find the reduced equation for internal energy as 9 nak t raised to 4 upon theta cube, and here you will find that the integration term has been solved up to great extent, okay, and it is simply x cube dx upon e raised to x minus 1. Again we can put here Na into k as r, and equation reduces to 9r t raised to 4 upon theta cube, integration 0 to theta by t x cube dx, okay, upon e raised to x minus 1. And now this expression can be differentiated with respect to t at volume V to obtain the lattice heat capacity, and after differentiating and solving we find this expression shown in this equation 11 as the Debye specific heat formula. Okay, so in this way we obtain the expression for internal energy here, and expression for Debye specific heat formula. And as we have done in case of Einstein's theory, here also we will test the Debye specific heat formula for two different temperatures, that is high temperatures and low temperatures. Now let us test it for high temperatures. For high temperatures, T is large and therefore theta by T is very small, and therefore we can put e raised to theta by T. Since theta by T is very small, we can neglect the higher power terms in theta by T, and we can write up to first approximation as e raised to theta by T is equal to 1 plus theta by T. And after substituting here in the second term in the square bracket, the second term will reduces in this way to simply 1. Now what about the first term? Since T is very large, so h nu by kt will be still smaller, that means x is small, and again we can put e raised to x as equal to 1 plus x. And after substituting here, we will find that x cube upon e raised to x minus 1 as nearly equal to x square. Okay, because here e raised to x minus 1, it will be equal to simply x cube upon x. So this is equal to x square. And in this way, for this integration term, we have this is 0 to theta by t, simply x square dx, that is x cube by 3 will be the integration, and after putting upper limit we have 1 by 3 into theta by t whole cube. And after putting the values we have obtained of first and second term in the specific heat formula, Debye specific heat formula, we find that it simply reduces to 9R in the bracket 4 by 3 minus 1, that is simply equal to 3R for T very greater than theta, and this is what we call as Dulong-Petit law. So Debye specific heat formula reduces to Dulong-Petit law at very high temperature. While what about low temperatures? Let us test the correctness at low temperatures. For low temperatures, we find that theta by T now tends to infinity. It not reduces to infinity, but it tends to infinity, and consequently the second term in the bracket of equation 11, so that reduces to e raised to theta by t, 1 upon e raised to theta by t, that means e raised to, so 1 upon infinity, and whole term reduces to a very lower value near to 0. And what about the first term? In first term we have to put here theta by t as infinity, so this will be the limits 0 to infinity x cube dx upon e raised to x minus 1. So as it is a standard integral having value pi raised to 4 upon 15, so after putting these values and solving, we will find that Cv equal to 12 by 5 pi raised to 4 r upon theta cube into t cube. So important is the factor t cube, that means Cv is equal to some constant into t cube for low temperature, that means Cv is proportional to t cube. So t cube law, as we have found in the experimental fact of testing of Einstein's formula, is proved by Debye, that according to Debye theory, that Cv is proportional to t cube at low temperature. This is famous by the name Debye t cube law. And if you are looking at the figure here carefully, you will find that the solid curve represents the theoretical values obtained by Debye's formula, while the empty circles represents the experimental facts, experimental values of specific heat. And you will find that for all temperatures from higher to lower, okay, so here the experimental facts, experimental values match well with the theoretical values obtained by Debye's theory. Hence Debye's theory holds good for high temperatures as well as low temperature. So in this way we can have three different theories. We studied three different theories, that is number 1 classical theory, number 2 Einstein's theory based upon Planck's quantum theory, and Debye theory, where okay, and it has been observed that according to classical theory, the specific heat of solid is totally independent of temperature and it is constant, that is equal to 3R, okay, at all temperatures. And experimentally this theory fails for low temperature, though it is correct that the specific heat of the solids or lattice heat capacity is equal to 3R at room temperature and higher temperature. But classical theory fails at low temperature due to its consideration that each average energy per oscillator is same. The discrepancy was the solution of discrepancy was attempted by Einstein by his theory, that is Einstein theory, and again he considered the oversimplified model due to which the theory fails at low temperature, where Einstein predicts that at very low temperature the specific heat is proportional to exponential of temperature, while experimentally it was found that Cv is proportional to T cube. And finally it was Debye who considered the coupling between the vibrating atoms, and he considered the solid as a continuous elastic body in which the energy resides in the elastic standing waves traveling with the velocity of sound, and he derived the specific heat formula which holds good for high and low temperature also. That means at low temperatures Debye proved Cv is proportional to T cube, and in this way we conclude today's lecture. Thank you very much.